Yeah, today no one is joined, so I'm waiting for someone who join. Then I will explain. Yeah, no one today no one is joined, so that's why I'm waiting. Not started the class yet. Yeah, am I audible, guys? Guys, am I audible? Oh, yeah, today that you guys will join so late. So okay, I will start the class. Okay, slides is visible, guys. Oh, okay. Now it's okay. Now, yeah, whether it's visible or not. Okay, thank you. Yeah, our first question is that's content. In this lecture, also that will cover some the reducing agent, that the rest amount of that reducing agent that will be discussed in the NPTEL classes. I will discuss some problem related to that. Okay. In the first question that we have that the cis that bicyclic ketones, and that the second question we have that the trans bicyclic ketone, and we have the lithium borohydride, and also you just check instead of that the hydrogen in this case they have substituted with secondary butyl. This is why, because that it's to make some the bulkier bases. That's why that we can design our base in such a way that we can attack selectively from that one phases as compared to that other phases, because in that cases the selectivity is very good as compared to that's where you have only lithium borohydride or that sodium borohydride, that any kind of the lithium aluminum borohydride. That's why the derivation of any kind of reducing agent that they have tried with the different type of that the any different bulkier reagents, but still that the borohydride that this is LiBH, the hydrate was there. That's why that hydrate will that reduce our functional group to their corresponding that the reduction product. In this cases, what will happen? You see that in the first cases, the attack will be happen from the below above phases only. But in the second cases also, the attack will the attack happen from the above phase. To show you how the it will happen. Then whatever that this BH bond will be there, yeah, that will be attacked to our ketone. Then only we will get our the product. But when that you have cis junction, this one is that a cis junction, and when you have the trans junction also, in that particular cases also that you are attack is from that the above sides only. That you will get in that the both cases your alcohol from that below sides, right? And here that's your hydrate, that whatever the hydrate will be from above sides only. That the both cases also. But to explain that the why that this one is that the product, I will explain. If you want to see that the chair conformation of that the any kind of cis that the more stable conformation for that the cis, first we will see that's our the ketone, the cyclic ketone in a the chair conformation. This is our cyclic ketone, and we have to make sure that among two that chair conformation, that which one conformation is more stable, the first one or the other, or the second one. In that case, you will see that the first one is much more that is stable as compared to second one. Why? Because in that the first one you will see that this methyl group that will be in our the equatorial position as compared to the second that chair conformation state, okay, or methyl group that will be in the axial position. That's why first one is there much more stable. But the rest of the amount that will be in chair, that are both that cyclohexane ring that will be present in the chair conformation. So the major difference is that the methyl group one. Then only we'll select that the which one will be that the which phases will be the much more the available for that the hybrid attack. That's whether from that our axial attack or whether or that the equatorial attack. In this case, you will see what okay then these phases and these phases. Among that these phases because if you attack from that this equatorial attack, then what will happen? Then it will causes a steering hindrance with that this all that cyclobutane sorry that cyclohexane. But if it comes from that axial position, then it will causes it will causes only that the 1,3 gauge interaction with that the cyclobutane. But if it is comes from that the equatorial one, then it will causes that the diaxial interaction with our that the whole ring. That's why that's our above attack is much more feasible. That the axial attack is much more we call them as a feasible as compared to our equatorial attack. That's why the attack will be from the hydrate. Whatever that the BH, this BH is that the hydrate transfer that instead of that the LIBH for that we have LIBH and that hydrate is nothing but the reducing agent here and that hydrate will transfer through axial. This is only because that the axial faces is much more that facile that the less steric hindered as compared to the equatorial face. That when you will draw any kind of if it is that is a cyclohexane ring, that the cyclohexanon or bicyclic or that the both 5 and 6 member bicyclic or both 5 member bicyclic also in that state that you can draw their the most stable favor conformer and then you will decide from which one is more accessible for that the reaction. And after that, if you transfer on that, then you will get this product. And also for trans one also the same thing, but in that the trans cases, that's when it will be trans. The most stable conformation is that methyl has to be in the axial only because that's our ring that both the ring that both cyclohexane both that the carbon that will be in that the equatorial, but in that the first cases that will be the one is equatorial and one is axial in that the both conformation if you see, and the major difference in that the first conformation is that the methyl, but in that the second conformation for trans cases what will happen, that's our methyl group has to be in we call them as axial. Why? Because our that the cyclohexane ring that has to be comes to in equatorial position to get maximum stabilization as compared to our methyl ring. If you put that our methyl group in equatorial, then here that that the both cyclohexane ring that will come in the axial, and that is not possible. For a compound for that trans compound, that's why for that any kind of trans compound that it will be always in chair conformation that if it is in 6 member, and in the particular cases also that we have to be decide from which one is much more feasible, whether uh, first erase then I will erase that which one is much more feasible. First you will tell that which one is much more favorable, the axial and equatorial one. In this particular cases if you see that's our attack is from that equatorial position only. If you see there, that's our attack is from that the equatorial one as compared to axial. That if it is comes from axial, this one is axial, this one is equatorial. That if it is comes from axial, then it will causes the steric hindrance with this methyl group. We call them as the 1,3 diaxial interaction. Okay. But if it comes from equatorial, then we call them as the 1,3 gauge interaction. In this particular case, that what will happen that it has to be attacked from our the equatorial attack and we will get our axial alcohol. But the stereochemistry in that the both cases that will come as a set. But the attack is from that the first cases the attack is this is axial hydrogen and this one is equatorial hydrogen. That is the difference. From which cases the attack will be there. Okay. Okay, guys, do you have any doubts in the slides? That how that the Angela attack? Yes? Okay. Okay, then I will proceed to the next slide. Yeah. Thank you. Uh, Yeah, this is our second questions. So I'll see. In this case, we have that the conjugated, you will see that we have conjugated that the alpha beta unsaturated ketone, and this one is the much more conjugated as compared to 111 here, 211 is there. And we are using the tosyl hydrazide that in presence of that sodium. Yes? Okay. Now it's okay. Now it's okay or not? Okay. Because uh, that's when I'll use that the pen option now. In that case, it causes some problem. So that's why I'm asking whether the slides is visible. That's the next question. That's we have the alpha beta or saturated keto and also the conjugated one, more conjugated one. And we are using the paratoluene, the hydrazide, in sodium borohydride, and we have that the acidic solvent. That's here we are using that. In some cases that we are using the deuterated acid, and in that in another cases that we are using that is sodium, the deuterated sodium borohydride, and that the normal acid. Then what will be that the expected product in that both cases? Do you have any idea? Suppose that we don't have any that deuterated one, and we have only that paratoluene sulfonate hydride, sorry, paratoluene sulfonate hydrazide and sodium, we call them sodium borohydride along with our acetic acid. Then what will happen? So what is the general reaction? That if it reacts with keto or the alpha beta unsaturated keto, what will happen? Yeah. Okay. And how? Yeah. What will be the product you will get? Yeah. Yeah. The double bond will migrate and the keto will be removed. The migration always the isomeric alkyne, we call them alkene will be part. But in this case, yes, we have deuterated solvent and deuterated that sodium borohydride. Okay, the mechanism we'll see, but we have that we call them deuterated the acidic source and the deuterated as the reducing agent also. But in that the first cases we are using deuterated that the reducing agent, the sodium borohydride. Then what will be that the product that we will get that the isomeric alkene that we got, but in which cases the deuterated will be there. Maybe the option may be that maybe I have written that maybe it's somewhere wrong also I don't know. But can you tell whether the deuterated that will comes from which position? That whether the deuterated will come in the first cases, in A cases, what will happen? Whether the deuterated because this one is that the this will transfer to this one and the keto will be removed. Okay. Then whether the deuterator whether it will comes here or that the whether the deuterator comes here. In the first cases, whether the deuterator will comes in the position 1 or 3. Or in the second cases also, that's whether the deuterator will comes in first and do you know? Okay, then I will proceed. Yeah, tell you what will happen. That's when and that the why also I will explain that why that will get that the particular type of deuterated one that instead of others. From the mechanism only that we can say that. We can't say that we can memorize that how it will be for, but for understanding that we should know that how it will for. What actually happened? That's when we have the tosyl hydrate that then it will react with our keto and it will get a trans one because here I am drawn that cis one, but we'll get the trans one. Okay, yeah, that whatever I am reading that this one is the cis one, but we'll get trans one. So and after that, what will happen? That's whatever your that is sodium borohydride source, the hydrate one, that will be, reduce our that the image, that what are that our the we call them as hydrogen, it will reduce our hydrogen, the corresponding, and whatever this hydrogen, the after reduction, then this one, that this hydrogen will be there in this cases, you see, in this case the hydrogen will be the, yeah, this will be our the hydrogen, and our deuterated will comes here. In this case, the first cases, that's our deuterator. That when you will use that the deuterated sodium borohydride, so deuterator which comes at when the attack will be happen. That we call them as hydrate. Attack will happen to the image. In that positions only, we will get deuterated. Like that, in this position, we will get deuterated. After that, what will happen? That we call them a sigma-2 type of reaction will happen. Our N2 group will be removed. That N2 gas will be removed, and this hydrogen will migrate. This one data will happen, and our alkene will be migrate to the corresponding isomeric alkene, and we will get our call them as the deuterated in this position. That we call them as a one positions. But in that another cases, what will happen? We will get our deuterated at this position. In that other cases, why? I will explain. The first as such it will fall, but that's we are using that the deuterated solvent in these cases, but still we'll get the deuterated here because there is no hydrate source here. That's the we call the deuterated source. Then it should be only attack with from that our call the major from sodium borohydride also. But before that, what will happen? That's this particular cases. The rate of reaction for that we call them as the exchange, that the exchange proton of that the NH proton to our acidic solvent, that deuterated acidic solvent, that is much more faster than the our that we call them as a deuterated, that the our hydrate attack to our the hydrogen. Whatever that the reduction will be happen, this reaction is much slower reaction. We call them this reaction is much slower reaction than as compared to our that the proton exchange reaction, because proton exchange reaction is much more faster reaction like acid base reactions. Okay, so proton exchange reaction, and generally why it will be formed that the ND bond as compared to our N deuterated bond as compared to our NH bond, because that the bond between nitrogen and deuterated is much more stronger as compared to our nitrogen hydrogen. Okay, that's why that it will always form that the deuterated one, then only our hydrate attack will be happening. Then after that we have that the sodium borohydride, the hydrate source, this particular case, and after that what will happen? Then whatever deuterated, but in the first case we have hydrogen, but in this case we have deuterated, and that deuterated will attack here, and we will get a deuterated here in that the in our three position. The instead of deuterated, that if you use tritium, then you will get that the tritium. Yeah, it will defect. That the which one you will use that which it, but it is very difficult to that synthesize that the tritium based the acetic acid. That tritium based acetic acid is very difficult to synthesize. So then how will synthesize that the deuterated the acetic acid, like from acetic acid that we put that any kind of that D2S solvent, the reaction for that overnights or that sometimes, then we'll get the deuterated exchange between that this hydrogen and deuterated will be happen, and we'll get that most of the acetic acid as a deuterated solvent. And also there is other source of that the deuteration will be there, like some people they are using that the methanol D4 also, that to deuterated that any kind of acidic hydrogens, the any kind of that the we call it the acidic hydrogen or that the we call them exchangeable proton, we call it the exchangeable proton is there, then there is possibility of that the deuterated the exchange will be happen in that case. That it was any like OH bond or that the, we call them as a nitrogen H hydrogen bond. In that particular cases, what will happen that it will use any D2O or like methanol D4, then it will exchange their proton to their corresponding ND and or the OT to their corresponding deuterated that the nitrogen deuterated, because the nitrogen deuterated bond, these are the much more stable bond that as compared to our nitrogen hydrogen. Yes, any problem? Okay. 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 Do you have any question in the slides? Okay. Then I will proceed to next one. Yeah, this one is our the bicyclic, the alkene, interested we call them as the borin also, not borin type of. And this one is that the instead of not moving. Okay, okay. Now you check the whether it's visible or not. Now, hmm, now it's okay. Yeah, yeah. I'm changing the slides also sometime. Okay, so okay. Yeah. In this cases, the reagent we are using, do you know that this what is N2H2? Yeah. Generally, hydrogen that will be stay as a normal hydrogen or with what? Generally, hydrogen they are stay as a hydrogen hydrate. Okay, the stable that they should stay as a hydrogen hydrate. Huh. But in these cases, what will happen? That hydrogen hydrate, that's whatever we are using, that the in presence of copper chloride. You see, this is copper chloride that we are using. Ah, then what will be the expected product? Then what will you expect you? Is there any kinds of yeah? Method. Then from which side the atom will happen? How it will react? How hydrogen will react? Yes. How? Yeah. The whatever that top side will be attacked, that's okay. But how that this hydrogen will react? The in presence of copper chlorides. Okay. This one is okay. That's your attack is from that above side because above one, that's the top faces is we got them as the less hinder as compared to other below faces. Okay. That's one I understand. But that how it will react. How that you will say that your double the attack will happen. How? Because that whatever hydrogen, because then we have what? The nitrogen, nitrogen, and we have that this hydrogen and the another hydrogen. Okay, then how it will react? That's my questions. So it will directly give the hydrogen. How it will form that the six member ring? That's how I will explain. How it will form six member ring. No. Okay, okay. Yes. Will take time and also that will say if it is possible. How it will form. The general reaction what will happen? That's we have copper chloride. Okay, because of this copper chloride only, that's whatever that the N2H2H4 that it will be converted to our corresponding N2H2. Yeah, we call them as the diamide. This one is our that the reactive reagent that will be react to our the alkene in a we call them as a six member transition state that whatever it is. That's why this reaction we call them as a stereoselective. That there is specific type of reactions. That only particular phases only both hydrate will be transferred. It's not like that only one hydrate will be transferred. Both hydrate will be transferred. How it will transfer? This one is nitrogen and this one is nitrogen. Okay. This one is our hydrogen. This one is hydrogen. If you have any alkene, uh, then how it will react like that. Then the nitrogen gas will be evolved like that. Okay, this is we call them as a six-member transition state. This six member. Then if you don't have this naturally bond, then there is no chances of attack will be happen. That's why copper chloride, that's what it will do. That it will remove hydrogen gas and it will form fast here that is the diamide, then only your reaction will happen. Yes, yes, yes. Okay, I will show that the material. Also, I have discussed some that the other kind of the stereochemistry how it will be for. In this case, what will happen? The one methyl group is missing here. Okay, so this is our methyl group. So the one methyl group is missing here. What will happen? That's we will get this product as a the 92%. The another product we got as a the 8%. And what will happen? That in presence of copper chloride, that the dichloride, that this one is formed as a diamide, and that diamide will react with that. I show you that how that the mechanism will be happen. This is hydrogen, and this is hydrogen. Then if you have any alkene one, then it will attack, and then attack, and then okay. And our nitrogen gas will be involved in this reaction. The gas evolution will be reaction. In this case, the stereochemistry is that from the bottom phase is more steric crowding as compared to our the top phases. This one is our top phase, and this one is our bottom phase. That in this particular case, that the bottom phase is less steric. Suppose that this dimethyl group is there, and we have, yeah, I will draw some other kind of alkene. So we have only this alkene. Then which attack will be that much more favorable? That the top phases is bottom phases. Top phases is much more passive. This is only why the reason is that because in that the top phases, yes, yeah, you are not, you are audible but not clearly. That's maybe your sounds is very less. Okay, okay, I will explain that. What will happen that when it will comes from uh, that any kind of this system that if it is a ketone that any other that instead of alkene that if of ketone also or you have any reducing agent that any kind of reagent that's when it will come from that the above that the top facet then what will happen that it will causes only repulsion with one carbon, but when it will comes from the below facet then it will causes with that this both carbons. See, that's why that it will always favorable from the top facet. But suppose that your top facet is blocked with the other two dimethyl. Suppose that instead of the two dimethyl group, it's a both phases, then your attack will be from that the bottom phase. Then it will depend that how much type of substitution and the substitution is that the whether it is methyl or the ethyl. But in this case, in that cases particularly, you will get some mixture of compound like the one is major product and another is that the minor product. You won't get the selectively only the one is 99% the greater than like in this particular cases you will get the 90, but still you will get some that's the 8%. That's the thing. That to get completely radio selectivity, then you have to be use such type of system to get that the complete radio selectivity of the DS. Okay. Then we'll move to our next slide. Slides visible this time or not? Okay. Yeah. When I use pen now, then it causes some problem. But okay. Mhm. In the first cases, we'll see that's how it will react with alkene. That's whatever that hydrogen hydrogen that in presence of any oxidizing agent that it will oxidize that hydrogen to their corresponding diamide and that diamide will react. But in this particular cases, what will happen? You see, that's we have that conjugated the alpha beta unsaturated carbonyl compound, and we have the hydrogen hydrate and a base also that we are using, and we are using that at 200 degrees Celsius. And this is a very high temperature. Nowadays, that if you have any kind of let's call them very big molecule, then molecule content that's of sensitive that the carbon that the some sensitive bond that if you use that same condition to their corresponding their product, whatever the product will be happen. In that case, what will happen that if you use that 200 degrees Celsius, then maybe it will break, or there is some other kind of that the reaction will also happen also. That's why that this kind of after this is a disadvantage, but still that we can use for that small molecule, and also there is some derivatives we call them as a modification of that this type of reaction is there, that we can put that the reaction in a the room temperature also by using that the different kind of condition by changing the condition. But what will happen in this particular cases? Yeah, this is a name reaction. Do you know what kind of name reaction is this? The last one is that the this one is what kind of name reaction? Yes, yeah. This one is that the basic condition, but generally what will happen in we call them Wolff-Fishner that the reduction that if of any carbonyl compound, and if it is that in the yeah, yeah, whatever that it will got you will get your alkane. Okay, but but in this cases what will happen that you will think that we will get this one. Okay, so whatever that product will be, you will think that we'll get this one. Huh. Yeah, this alkene is already present in the reaction mixture, na? That's okay in the structure. In this case, that you will get ACH3. That's you are saying. What are the product that I will draw again? We will see carefully. The product that we are expecting this one. This one is converted to CH3, the alkane, and we have that the 2GM dimethyl group, and this one is the methyl group. Yeah, this will be our the product that we will expect that the any other kind of product that's will fall. Yeah, you only or that the others. Okay. For the this slide or that the other slide is also. No, no. That when I started the class, that yes, from the started of the class. Oh, then you should tell. Okay, okay. Yeah, I'm drawing, but I don't know. That's why I think that's yes. Okay. That from the that we call the start of the class that you are not seeing any kind of drawing. Okay. How is this possible? Is it really possible? Okay, then I will explain through that the ledger point only. From the ledger point only, I will explain. Because I don't have any that the iPad for that pen stand, because so when I try to draw in but then I think that PowerPoint, but okay, if it is not. What actually happened that instead of that any kind of that if you have that the normal aldehyde and ketone, wait. Now my drawing is visible or not, that whatever I draw. Okay, okay. The laser pointer option is there. Whatever that the laser pointer option. Okay, okay. Yes. Now it's slide is visible or not? Okay. Then that whatever that the conjugate ketone and aldehyde that undergoes on that we call them as the whole Kirchner reduction that will get whatever. Yeah. Oh, okay. Why? I don't know why it will happen like this. Okay, but okay, I'll present again. Wait. Okay, entire screen I will present. Now it's visible in the entire screen. Okay, I don't know. Okay, my drawing is visible. Oh, okay, okay. Yeah, slides is moving now. Okay. Yeah, what will happen generally? That's when we have any keto, that's we have keto or that the aldehyde, the any kind of that, that it will convert to their the alkane. So we call them as the Ullupissner reduction reaction. Generally. But in that particular cases that when we have conjugated alkene, sorry, the conjugated that the aldehyde or ketone, in that particular cases, what will happen? That we will get our corresponding isomeric alkene either or our that the cyclic alkane also will get sometimes. Okay, in some exceptional cases, we will get a cyclic alkane. But in this particular cases also that instead of this conjugated that generally that people what they expect the product that this product they will expect. But instead of this product that we will get the isomeric double bond will happen. So whatever this one, this double bond will happen. And we will get this product. That the exo double bond, that the exo double bond will get. This alkene that will be isomerized to their corresponding that methyl group and we will get a exo double bond. How it will form? In the cases that's we have base, that's we are using any kind of base in this cases, that the general kind of reaction called them as the mechanism of Ullpissner reduction reaction, that we have a strong base. Any kind of, in this particular cases that we have ethoxide, sometimes that you can use the more stronger bases like sodium taught butoxide, potassium taught butoxide. In that cases, the temperature you can perform the reaction at room temperature also. That's by using that kind of that the strong bases. And we have that the base, yeah, that will after that this proton, then it will form the nitrogen negative charge. And what will happen? That this double bond will be transferred to the corresponding, and again that this nitrogen that will after this nitrogen that will after this proton. First it will transfer, then this negative charge will comes here, then this negative charge that will after this proton. Then it will forms a negative charge on that the nitrogen again. Again, that this one will form that the nitrogen, we call them as a nitrogen gas, and we'll get a carbanion. That's carbanion. And from that carbanion, that we'll get our corresponding alkane. But in this particular cases, when you are that this kind of system, in that cases, what will happen? That instead of that this negative charge will form here, that it will shift it to their corresponding alkene. That's why our double bond, the whatever that the double bond, that will be isomerized to their corresponding the less stable, or that if it's possible also in some cases that it will be there the corresponding more stable because of this carbanion formation. Okay, this carbanion formation in that the intermediates during that the mechanism of that the reaction, that's why that it will form that the we call the corresponding isomeric alkene. Always you will get that the isomeric alkene either, or some cases also that you will get, you'll see that this is that the we call them as the exceptional cases. In this particular cases, what will happen? That instead of isomeric alkene, that will expect someone maybe will expect that this kind of product. Okay, this product that we should get in this particular cases, but we won't get this kind of product. We'll get a that a cyclic alkane. A cyclopropane ring will be for and will get it. This one is methyl, and this one is methyl, and this one is also methyl. Yeah, I will show through the mechanism that how we'll get. That's when we are using the hydrogen hydrate, then what will happen? Just see. That's whatever that this five member ring will be for first in this cases. So with the nitrogen, and it will form a five member ring. That instead of that the nitrogen leaving group, that the, in this particular cases that will form a this is and we call them as the exception cases. Okay. Particular cases that instead of the nitrogen gas will be removed, that it will form a five member ring. That the we call the five member transition still. Because this five member transition that the ring that will be more stable as compared to the other nitrogen. After that, what will happen? That it will give them more heating. In that particular cases, that it will form that the removal of the nitrogen material through a radical. They believe that it will goes under the radical mechanism and you will get a cyclopropane. That's when there is a possibility of the cyclopropane that will look for that the cyclic alkane. For most of the cases, you will get we call them as isomeric alkane. But in some cases like that, this particular cases, that they have reported that instead of cyclic alkane, that the alkene that we call they get that the product as a three-member cyclic ring. And for that we call the more details that you can check the Carather books. The Carather books that we call them as their journal citation will be there that you can check that how they will get that this product. And also they got some product that the byproduct of alkene, but majorly they got this cyclic product. Okay. Yeah, this is the condition that when you have alpha beta unsaturated ketone, in that cases either you will get isomeric alkene or cyclic alkene. Okay. Yeah, any questions, guys? Okay. Then this is our yes. Any questions? Yes. And then you should ask now. Okay. It's open that during the class also you can ask that if I'm not saying any question, then you can ask. Okay. Yes. No. That's if you have any question, then you can tell. It's not a problem. Oh. Yes. Yes. More and DMS. No. It will only reduce the carboxylic acid. You'll see. So we have some question that it will reduce carboxylic acid, and also that's other thing that I'm not sure. That's confirmed because that I'm not completely read anything. That's whatever because I'm preparing for that the classes only, but I'm not still confirmed. I will check and I will tell you. But in the upcoming slides, we'll see that yes, no, the yes, yes, maybe not, but maybe is this possible because I'm not confident. Yeah, whatever that if you are using that the 5 mole percent, that's what because this is question that because if I don't know means don't know because I can tell you that whether the reaction will happen because if I don't know then how can I tell you whether the reaction will happen? But I will check and I will tell you because that's you are asking that the in presence of BS3 EMS that the borate that with that a 5 mole percent of sodium borate maybe it will be possible because sodium borate yeah it will reduce, but I will check and I will because that kind of condition I have not seen yet. Okay, that's if you have seen, yes. Maybe this one is from that the research things. Okay, okay. The next one is okay, okay, in मतलब which assessment can you tell that the which week one? Then I will check. Okay, third week assessment. Okay, I will note the third week assessment question number. Okay, okay. Yeah, I will check. That sodium borohydride one, na? Okay, I will check. Because, okay, sorry. That the birth reduction, okay. That the week 3 assessment, that's okay. The birth reduction, because, yeah, these are, whatever the assignment, uh, these are made by my lab mates only, okay? That's my two senior lab mates. They make that because that whatever the professor that, yeah, he's my own supervisor in PhD. So I am taking that the whatever the question discussion for that one, and the TA they have assigned for from the NPTEL only, my lab senior also. So I will discuss with them. Yeah, yeah, okay, okay. Question number 5. Yeah, I will discuss with them in the next class, that I will tell you that the why that if it happens or not, and also that in there is a question forum also. In that question forum also, they will answer that. Yeah, you can ask if you have any question related about that, that the assignment, or also that class also, whatever the class they have, you can ask the question in classroom forum. That's it. Maybe you have login ID for the NPTEL work. In that cases that you can ask question that in that particular case why it will be happen. Yeah, they will. Yeah, these are two people. They will explain. That's if you have any question regarding the assignment, and also your the 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 lecture slides, or the during lecture also, that maybe if you have any doubt that you can ask. That if you want to that if you are watching in the recorded lecture, whatever the recorded lecture is, yeah, that will be given by our NPTEL team. In that particular cases that you can ask also. That in that particular timing, that there is some problem, so I didn't understand, that you can write that, that they will explain. Maybe you will get some after some time the reply, but you will get. Okay. Yeah. Okay. Okay. Yeah. Okay. Or whatever that sodium borohydride one, that's what we are saying, that I will say. Okay. I'm not confirmed yet, so I can't say that's whether it is possible. But in this cases, that we have that instead of in the first cases we have what we have the sodium borohydride, sorry, sodium borohydride. But in this particular case, that's we have sodium cyanoborohydride. Okay, and the same condition is also there. The paratoluene sulfuric hydride in acidic acid. Yeah, what will be the expected product that you will expect? The option that you will say, because we have another kind of that the we call them allylic acetate also will be there. The whether it will react with our call them allylic acetates or not, that it will only react with our the keto one. What will happen? Maybe this question is from 2019 July, I think June or July, that net question. If I'm not wrong, because I made these slides from 2021, so I'm not confirmed, but maybe this is a question from the net 2019. At that time, I have appeared the question, so I know. See, okay. Ah, then you will say that whatever allylic acetate that will be reacts with our, whether it will react or not. The whatever our this one, this part, it will react with our sodium borohydride with any kind of reagent, that whether it will react or not. That it only reacts, that you are saying that the everything. Okay. That's the thing. That these are not even that this kind of that the we call them allylic, that the we call them allylic acetate. In that case, that it won't be that the react with any kind of that the reducing agent, or that the acidic source. But instead of that, OAC, that if you have OH, in that particular case it will reacts. If you have allylic alcohol, in that particular case it will react, because that it will form a carbocation by removal of water. And also that if you have OAC, or the any OR, that we call them as living group, in that particular cases what will happen, that it will form a, that if you use that any kind of palladium metal, and that the rhodium metal, we'll see in that further classes, the palladium and rhodium metal, in that particular cases, that will form a palladium allylic complex. Particularly palladium cases that you can use, or also that iridium also, not rhodium, I am not confirmed, But palladium and iridium that reacts with any kind of allylic alcohol or the allylic acetate, in that particular cases that will remove the acetate group or the OH group that as the water or acetic acid, and it will form a carbocation. In that particular cases, that if you have any kind of nucleophile, that will reduce. But in this particular case, we don't have this call them as that kind of scenario. That's why our reaction only reacts with our alpha beta unsaturated ketones. So we'll get our corresponding isomeric alkane. This one, the whatever the C option is our corresponding isomeric alkane. We'll see the C option as this one is our isomeric alkene. Then instead of this alkane, yeah, it will transfer and our keto group will remove. But- And the mechanism is like from the for that the first one. That this is a call them as a cis member transition state also. This one is we call them as a 1,3 sigma tropic rearrangement will happen and we'll get our corresponding alkene, isomeric alkene. But in this particular cases, we got that the more stable alkene. In some cases, also you will get less stable alkene. It will differ. But in this case, that we are using the lithium borohydride and acid, and also in the first cases where we are using that borane, the DMS. That if you use only borane, then it is not possible to that reduce ester. That's what we were asking now. If you only use borane, then it is not possible to reduce ester. That's one I confirm. Okay, but you are saying that the sodium borohydride has a 10 more percent or 5 more percent. I don't know that's whether because that sodium borohydride, yeah, it can reduce somewhat. It can reduce. It won't give that the for them as a 100% or that 60-70%. Maybe it will give the 5 or 2%. Maybe like, but for sure I will check that kind of condition. But in this particular cases, what will happen? What is that? The question is that what is the relation between that the P, the whatever the product P will be formed and whatever the Q product will be formed. What is that the relation? Ah, ah, okay. Yeah, whatever electron you will get. Okay, okay. Okay. Yeah, I understand. Yeah, whatever she has. Okay. Ah. Then what will be the relation between P and Q? Okay. I will show the structure also. Don't worry, don't worry. I will show the structure. Whatever the final product you will get. Okay. Yeah, these are the structure. Then what is that? We call them as relation between P and Q. Then what is that both structure? Huh? Then what is this? Then what is this? Okay. Others? Anyone? Okay. Then you are not saying these are identical. Yeah? No positional answer. Yeah. 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 Huh? Yeah. These are different molecules. Okay. That whatever that's you are saying that this one is correct. These are the both are different molecules. These are not same molecules. Okay. If you check also, that you will find out that whether there is a that in the NSA molecule that you will get that plenum symmetry, but you won't get. If you want to check also, that after the class that you can check that I will provide the slides in the class also, you can check. Not you, because most of the people they have to watch that recorded in the lecture also. Yeah. But in this the next cases that we have whatever that's the hydrogen, sorry, point, the hydrogen hydrogen chloride, and also we are using bases also. But in this case, that instead of the alpha also the ketone or whatever that, in this particular cases we have that keto, but we have in the next position we have an epoxide. Okay, then what will happen? Anything, any idea? Okay, CH2. Then the product will get, this one is our epoxide and methyl. Then we will get like that. This product will get, really, anyone? No, that we won't get this product. That it will stay. This product won't. Because if that kind of reaction will be there, then why I will show in that the NPTEL classes? Okay, na? If I have some questions, then okay, okay. Then I was saying first that if I have taken some question, that's when there is some, we call them as some another kind of reaction will happen, or that's there is some special reaction will happen that particular case. That's why I'm taking that kind of question. The normal question maybe you will know, because these are you will get in some books also, that in every books you will get that if it's convert to from keto to like alkane, everyone will. But in this particular case, what will happen? Yes, yes, why not? No, that we want to do. The option is there. You just check. Yes, C is that the answer. What was, because if you see the answer, then it's C. This one is our answer. Okay, but how it will work? You know. Also, sorry. Yeah, you will see first what will happen. That's first it will form, and whatever who that's ketone with hydrogen, and their proton transfer will be happen with that the base, because we have the triethylamine transfer. Okay. After the what will happen when it will form that from diamide, that the nitrogen diamide to their corresponding the nitrogen, then it will transfer. Sorry, the bond between carbon and nitrogen that will break, and it will form an alkene, and our epoxide will, that's whatever that bond between carbon and epoxide, that will suppose that epoxide will be in that the other position, like in this particular position, or the other, any other kind of, we call them acyclic system. In that particular cases, there is chances of nucleophilic attack will be there. But in this particular cases, only the alkene will be formed, and our epoxide ring will open, and we'll get the, we call them as a retention of our stereochemistry of epoxides. Whatever the stereochemistry of epoxides will be, and we'll get our corresponding alkene. Instead of that, we were saying alkane, we'll get our corresponding alkene, and our epoxide ring will open, and we'll get our corresponding, we call them as allylic alcohol. The retention of the stereochemistry of the reaction with that the allylic alcohol. You see, this is nothing but a allylic alcohol. Okay, particularly this kind of that we call them as alpha beta unsaturated epoxides, that the epoxide, that the carbon epoxide, in that particular cases with hydrogen hydrate salt with bases, that we will get this kind of product. That this kind of ring often will be happen. Okay, yeah, any questions for this slide? That do you have any questions? No, no. That bicyclic, whatever the bicyclic is much more the unstable as compared to the alkene one. That's why it will always undergo through the alkene formation. That the ring will often, that instead of to form a ring. Oh, huh. In that particular cases, what will happen? Then we have hydrogen hydrate, also acidic acid and ethanol. And we have option also, because this time I have given some option, but okay. Option is not important, but what will happen? Yes, you have 2 to 3 minutes that you just take, and if it is not possible, then I will. The first option, the keto will be directly reduced, and in the second option, the keto will reduce to their corresponding alkene, and the third option, that is we call them as the isomeric alkene also there, and the bicyclic ring will break. What will you expect? Yes, first you will. Yeah, diamide only reacts with not ketone. You just see this one now. So whatever that is there. I'm when that okay, yeah, you just first listen first. That if you have alkene in that particular cases, we need the diamine to reduction alkene. Yeah, for ketone that we don't need the diamine. We don't need. Yeah, see. Oh, but whatever you say, I don't know that what is the answer because first I will solve, then I will tell you. Okay, but how that's the if you see if you tell that the C is the answer, then how the C will be answered? Yeah, please explain. That if you whatever the knowledge you have that you can explain, it's okay. Yeah, okay. Then how can you say that it will form that this C or D? That if you don't solve, then how can you say? Maybe D also possible. It's not like only C also possible. Yeah, the ring will break. Okay, how the ring will break, I will show you. Yeah, first what will happen? What? This one, the whatever mechanism I will show you in the sketching also. First it will form, that's whatever this one. Now after that, what will happen? When it will form the nitrogen double bond, first the carbon nitrogen that will convert to their corresponding alkene, and whatever this bridge ring, because we have in that particular cases we have sigma star, we call them as the sigma star of our the carbon bromine bond. In the specific case, that's why this bond will attack to the sigma star and will get a alkene. This alkene will get this the instead of this more substituted alkene, this alkene will get this one, the product. In the cases that first bond will transfer to alkene, then again that this base ring will that we call them as attack to that the sigma star. Then for any kind of SN2 reaction, what will happen? That's whatever your nucleophile will attack to their corresponding sigma star of that the carbon and halogen and whatever that the X group that the living group will be there, then it will be attacked from that the 180 degree. That's why that your whatever that the living group that has to be present to their back side. Then only the rearrangement will be happen. Otherwise, only your that the ring will open and it will form the carbanion and it will after that proton to their corresponding acidic acid. So that from corresponding acetic acid and it will form a that CH. And if it is the alignment of that the orbiter, it has to be from that the 180 degrees Celsius. Then only your migration will be happen. For any kind of reaction, the orbital symmetry is much more we call them as important. When that you are in bachelor degree, that's okay. But when you comes to master degree, the orbital overlap for any kind of reaction is much more important. For we call them as any kind of carbonyl group, how that the orbital overlap will be there, how it will comes from whether that it will comes from the 90 degree or sideways manner, everything will be there. How it will react. That, suppose that you have any kind, we call them as carbon center. That if of any that the carbon and it is undergoes to that the alkene. Okay, and how it will react? which HOMO and which LUMO will react. All these things that you should read at least for better understanding. For the orbital in we call them as interacts. And for all that thing, any kind of the molecular orbital diagram for that, any kind of reaction, that you can check. We call them as a Cleiden book, that we call them as a new one, the new version, that you will get better that the orbital diagrams. That's whatever as compared to that the first edition. The second edition is good for orbital only, but for other things, the first edition is good. For we call them as a orbital interaction. That the second edition will be good. Okay. That's in that particular case that you will see whether this bromine will be from that the 180 degrees Celsius or others. Okay. Then only our transmission will be there. Yeah. Yeah. Nah. This is the acidic condition is not the Wolff-Piston reduction. The basic condition we call them Wolff-Piston. In acidic condition, we call them as another kind of reaction name. I forgot what is that name of reaction. In acidic condition, there is one name reaction. In basic condition, there is another name reaction. In basic condition, that we call them as Wolff-Piston. This one is we call them as what? I forgot. Okay, you will check that the name reaction. I'm not. If I don't know which don't. Then in the next slide, we'll check that some that's the asymmetric synthesis. That how asymmetric synthesis of that the reaction will happen. Okay. Yeah. In this particular cases, we are using some boron. You just see this one is our boron, and this is our keto. That the alpha beta unsaturated keto. This is a cyclic alpha beta unsaturated keto, and we have boron also. But also there is a catalytic amount that we are using this boron, nitrogen, whatever that's one. And this catalyst we call them as there is three scientists name. Shibata catalyst that I know, but there is two other that scientists is there, and from all that scientist name, yeah, yeah, who call them as the CBS Corey Boxy, yeah, Shibata catalyst, I think, if I'm not wrong. Okay, yeah, yeah, Shibata catalyst, yeah, yeah. This is that catalyst particularly only, but by using that kind of catalysis, that we can asymmetrically reduce our keto or the aldehyde to the corresponding alcohol. It is possible. Yeah, my general question that suppose that you are putting any kind of asymmetric synthesis reaction. Okay, that any kind of reaction, because nowadays people they are doing lot of asymmetric synthesis through CH activation, through organocatalysis by different kind of metal and ligand with the chiral ligand also they have tried. Okay, suppose that I have a two starting material. Okay. And I am using a ligand, that's whatever the chiral ligand, and I'll got a product, R and R. Then how can you determine that their stereochemistry? That is the which enantiomer will get? How you will determine? Do you have any idea? Suppose that you will get a product and you will confirm from the NMR that you will get a product. Yeah, yeah, that product will get. But how? And from a HPLC also that you will measure that the how much enhancer selectivity you will get. But which stereoisomer will be formed? Like that the whether in that particular cases whether your bond that will be from that is present in above or that the below one. Yeah, that one you have to be find out how you will find out. Yes, no, no, that's you can say that's from that optical rotation, that's whether a bond is from that the above side or that the below side. From which one is it is possible? Yeah, n- theoretical and also that the experimental also. That how you will predict. Theoretically, it is very difficult to predict. Okay, that for every kind of reaction, that for every kind of asymmetric synthesis reaction, that first everyone got that the corresponding product. Okay, so whatever the product they got, first they will take the best option for that is that the X-ray crystallography. From that the X-ray crystallography, that we call it will determine our stereochemistry. Okay, so if it is not possible that if you don't get crystal for that compound, what the people they did, yeah. They synthesize some that the derivative of that kind of compound, and they check that crystal. So if it is not possible, then they give that the relative configurations with that through NOG experiment. Maybe you know about NOG experiment in NMR. From that the NOG experiment, and whatever the proton will be there, they will give that the relative configuration. It's not like that they will give the, we call them as the whatever the absolute configuration. The best way for that getting the absolute configuration is X-ray crystallography. But maybe you know that the Sharpless epoxidation reaction. Okay. Why we call them, why Sharpless got that the Nobel Prize for that the epoxidation reaction? Because Sharpless also reported that the asymmetric version of that the epoxidation reaction. Okay. Then why he only got that Nobel Prize? Why the others those people they have performed that the epoxidation reaction, because some people they have discovered H2 H2 NOH, or some people they have discovered MCPBA, but why only that the Sharpless only got Nobel Prize? Do you have any idea? Yeah, because that in any kind of reaction that it is very difficult to predict that whatever the product will get. But still, that's from that that particular type of reagent they have using like DIPT, or that we call them as DET. From that, by if you use from that, from which side your attack will be firm, and you will get almost every cases that kind of product. Yeah, that is the beauty of we call them asymmetric surplus epoxidation reaction. That is the only reason he got the Nobel Prize. Yeah, that because nowadays also the whatever that you can say maybe you can predict, but that will be not that 100% sure. Okay, so that's why once you will get product, then you can explain the how you will get. But from that the Sharpley epoxidation, yeah, that is the beauty of the reaction. Do you know that the story behind who discovered that the Sharpless the accident we call them as the epoxidation reaction? Sharpless student, we call him a Kopustik is something name. His name is like that. Yeah, he discovered these reactions because of some politics in even till now also. It is same, but still now also there is some politics in that called them research also. That's why uh, whatever that I am doing, it has to go to that the credit to my supervisor. But still, yeah, that's okay because I am working under my supervisor. But the name only the Nobel Prize has to be given to the both one, that the Sarple and the student also. But only in that particular case, the Sarple got the Nobel Prize instead of that student, because that student only discovered. Okay, first he will take different kind of alkene. Okay, the story whatever I heard from one of my teacher. That's why I'm doing PhD first year. First, he took the alkene, the different kind of alkene, and they try with different kind of that we call them as the oxidizing agent with that the DT, or that whatever tartarate they are using, that the diisopropyl or diethyl tartarate they are using, and they find out that in particular cases which kind of product will be provided. He only find out. That's why, but still, didn't get any yeah, that is sad story because that we develop that. Suppose that you develop some reaction, but still that someone will got the credit. Then what does it mean? Okay, na? So that's it. But in this particular cases, what will happen? What will be the product that we will get? Yeah, definitely we'll got alcohol. Okay. Ah, ah. But how will got the alcohol? Oh, yeah, down one. That's one. That's whenever that you are using that CBS catalysis, then your attack will from that the above side only. In that the all cases. Okay. Yeah, this one. But how it will react, I will show you. I will ignore this one. Yeah, this मतलब look from above side the attack will be happen. Yeah, this is a मतलब that you can मतलब. But how it will happen? That's whatever that the this CBS catalyst will be there. How it will control their stereochemistry. The most important thing is how it will control that CBS catalysis. Because whatever we have, that the reducing agent, this one is our reducing agent. Yeah, that will bind to our, so whatever that the CBS catalyst, that the nitrogen one. This one, that will bind to our nitrogen. That it will coordinate to our nitrogen. And also that whatever that boron, that will be present. Whatever this boron, yeah, that will also coordinate. We call them as a Lewis acid. This is clear. Yeah, this one also coordinate our keto group, and it will keep such at a particular, that we call them as a distance, that it won't causes that the more steric hindrance with our that the large group as compared to our the small group. Okay, that's why. And also that's, if you check that these two 5 member, there is a exophases. That's in this particular case. I will remove the drawing first. Yeah, there is two phases. Pointer option. That if you see that the have both conformation, and also this one, this 5 memory, because this is not a particular that kind of shit. But if you see that the character books also, that in the book it is mentioned that you will get two phases. That the below phases we call them as the exo phases, and that the above phases also, that you will get the end of phases. Always from the below phases, your boron will be attacked, and also that your ketone has to be from the same phases only, because that's whatever our hydrate, that has to be transferred to their keto. That's why it has to come to their, close to their proximity, to transfer the any kind of the nucleophile or that hydrate reagent or the proton that will have, it has to come to their the proximity. That's why they have designed a such a kind of, because there was a catalyst that will contain the nitrogen and also the boron. This nitrogen that will donate we call them one pair of electron to their BS3, and also that's whatever that oxygen, the lone pair of electron that will coordinate to our boron. That's whatever that the boron will be there, that will coordinate. Then only our hydrogen, the ion will be transferred, and we'll get our corresponding product. And after that, what will happen? That if you do hydrolysis, then only your oxygen boron will be break. After that only, that if you do hydrolysis, if you don't do any hydrolysis, then your reaction will stay. We call them as a, at that step only your reaction will stop. That you will get as a salt. Okay, but if you do hydrolysis, then you will get your corresponding alcohol. Yeah, in the, that if you put that the same things as a, such a way that the whatever the explanation is there, then you will get this alcohol. Okay, and there is, yes, yeah, no, that's it's all the cases. That's what for my knowledge, what I know, that it's always attack from that we call them as the above phases. And why it is only because that's when it will bind to their exophases, from that both has to be from that the exophases, and whatever that your RL group, it has to be comes that the called the farthest from our this we call them as the endophases, whatever that the boron and we call them as the other kind of reagent will be there. Because of this both phenyl group only, this both phenyl group only, our attack will be from that the above. Suppose that if you skip this both phenyl group, then you will get that the mixture of products, that the both products. Yeah, yeah. Huh. Then you will get yeah, not down attack, the above attack will be happen. Not down attack, the above attack. You see, whatever that hydrate. Okay. In some cases also, that instead of CBS catalysis, it is not only applicable to that ketone. That's in some other also catalysis they are using that CBS catalysis. Okay, it's not only. Okay. Ah, yeah. Mm. Or for more understanding that for a for 3D view, that you can check for why that should be there. If you if someone for proper explanation why that below attack will be there, that the because in that particular case you will see that the re faces or C faces. Okay, that's when it will bind to that any kind of catalysis from that the re and C faces that you can measure. But how you will measure from that DFT calculation? First you have to calculate that when it comes from re faces, then what will be there the energy, and when it will comes from that the C faces, then whether in that particular case, that's whether your energy is how much. That in in which cases that your energy is less, that in that particular case your attack will be happen and you will get your flood. Okay, these are the general things in acid. Generally, DFT studies needed for to explain that for asymmetric synthesis that why only particular that kind of attack will be happen. DFT calculation. Do you know that what is DFT calculation? DFT, density functional theory. DFT. You don't know? Okay, okay. Yeah, maybe in we call them as a MSc. That's that you should know. But okay, we call them a density functional theory. Yeah, from the density functional theory that we can measure the any kind of transition state energy. That we can predict that the variety of transition state that the transition state energy, and we'll see that which the transition state is much more favorable as compared to the other transition state. That we can measure from that data. This is the computation, we call them as a computational part. Okay. As you are doing that the PhD, maybe someone will do it the PhD. So maybe he has some idea. We have that one more slides. Let's see in this case that we have, yeah, what kind of molecule is this? What kind of functional group will be in this, that the structure, that substrate? Yeah, what we have that the ether only. Okay, then what will happen? That's where you using the diethylsilane, this one diethylsilane hydride. uh, then it will, what will happen? And we are using that DCM solvent. This is the solvent. DCM is nothing. And we are using the Lewis acid. Hmm? Okay, we'll see. We'll see that. Yeah, this is the product we'll expect. How will got that product? Can you explain? Yeah, triethylsilane. Sorry, this is not diethyl. This is triethyl. Okay, that the triethylsilane, that silane are also sometimes reducing agent. Maybe that's you read about the silane based that the reducing agent. Have you seen that the have you read that any kind of the silane based reducing agent? Yeah, that it can reduce that generally acetal or hemiacetal to their corresponding ether and alcohol. Okay, whatever the corresponding that in presence of that's whatever we have silane, that in presence of any that the Lewis acid or acid, that it will convert it to their corresponding silane. The mechanism that you will say, because right now I don't have mechanism, but you'll say generally what will happen that if you have acetal and hemiacetal group, if you have any acetal hemiacetal, the in presence of silane and Lewis acid also it is possible, and also with that the normal acidic condition also it will possible to give that the ether group. In this particular cases, that it will convert break to their corresponding alcohol. Okay. And also, uh, in this particular case, you will see that we have variety of the stereochemistry. How many type of stereochemistry will be there? Sorry, chiral center in that the structure. How many chiral center will be there? Four, five. Yeah, five. Yeah, do you know that what is the difference between chiral center, CC, and stereogenic center? This is general question. Maybe stereo center. That yes. What is the difference between chiral center and stereo center? Yeah, both are same. Yes. They, okay, then you will go and check. Okay, these are not from our question, but that you should check. What is the difference between? You are saying that whether that the all stereo center is chiral center or not, or that the all chiral center is stereo center or not. Agree. Do you know what is? Oh, okay, we'll check. And one more question for you. That in the next class that you will answer. Okay. That if you join, so it's not mandatory. That if you want to answer, okay. Otherwise, in the next class I will tell. And one more question is okay. Okay. I will ask the one more question and forget. Okay. Question I'll recall. Okay. But, yeah, I will check. I will tell you in the next class. Okay. So I forgot one more question. But, okay, I'm trying to solve. Okay. Till I forgot. So okay. Then if I remember, then I will tell you the other questions. Okay. Better. But my request is that if you want to more in organic chemistry, then you should read that for every kind of reaction, their homo and LUMO interaction. That is the best thing. Okay. Then for a year better, if you are a MSc student, then you should read this homo and LUMO. If you are PhD, then it's okay. That because most of the time that you spend in like in lab only. Like me that I have in lab for 6:50. Then I came to room and I took the class. But after that also I'll go to lab and I'll work like that. For PhD student, that is that the sad reality. We can't say anything, but this is the sad reality that you have to work hard. Then only that you will get on that. In that particular cases, what will happen? That's if you have that every kinds of what will happen? Hmm. That's if you have any kinds of uh, in this cases, this one is acetyl group, okay. But in this particular cases, we have that the hemiacetal. That instead of breaking this carbon oxygen bond, that it will breaks only carbon hydrogen bond. Okay, this carbon hydrogen bond, the carbon oxygen bond will be break and we will get corresponding ether. Always we will get ether. Now we won't get that alcohol. That if it is break this one, then we will get alcohol. No, that you will get ether always. This one that you should remember from acetal and hemiacetal, we always get that ether. That in this particular cases also we got this ether. Okay, that if you are this ether and along with your alcohol that you will get. Okay, that's one is okay. But in this particular case, what will happen? That's your in hemiacetal cases that you will get the removal of this OH group to their corresponding. We call them as a hemiacetal to their ether we will get. The like we call them as from acetal that we will get ether along with alcohol. But in hemiacetal, that you will get only ether. But how the mechanism? Because I don't have mechanism, so that if you go and check the mechanism, if you don't find, then I will show you. Because of that, the lone pair of that the oxygen atom, Yeah, that will bind to that the our Lewis acid, and then only our ring break will be happen. And because of that, any kind of acids one, yeah, that will always helps to break our any kind of carbon and oxygen bond. So in the particular cases, OH group will remove, and in that particular cases, our this carbon and oxygen bond will be break. You will see that there is a carbon and oxygen bond will break. In this particular cases, and in this particular cases also, this carbon and the oxygen bond will break to their corresponding, that is ether and alcohol. Uh, And one more question. For general question, this is a the- suppose this molecule is मतलब R, okay? This center is मतलब R center, and this center is we call them as a S center. Yes or no? Hello, am I audible? Okay. No, writing is there or not? Yes or no? Okay. Okay. Suppose, do you know that the concept about pseudochiral center? Huh. Can you tell that what does it mean by pseudochiral center? Pseudochiral center. There is chiral center, you know. Pseudochiral center. Yes. Pseudo. P S E P S. Yeah. Pseudo. Maybe the okay. That pseudochiral center we call them those chiral center. In the chiral center, that if the chirality, that because of that movement of that the molecule, that if the molecule will be movement in that particular cases, that like that if you have two same chiral center, like same group, in that you have this one carbon is one, this one is two, and this one is three, and in all that carbon that you have the four different type of groups, that in that particular cases that you have only that's H and that are so whatever that, but in that particular the carbon 1 and carbon 3, that you have two different kind of group, a like that the two different kind of chiral center, but this chiral center contain, both chiral center contain same type of atom. Okay, that in that particular cases, that if you have configuration of both that carbon, if it is RR, that if it is RS, and if it is SS, in that particular cases, the chirality of this carbon that will depend upon the chirality of this carbon and this carbon. Okay, yes or no? The chirality of second carbon that will depend upon the chirality of first one and second. Sorry, first one and the third one. If it is RR, then this carbon is not chiral center. If it is both one is RR, because in that both cases that you will get RR, or if that both one is SS configuration, then here some carbon 2 is the not a chiral center. But if it is R and S with that same kind of that the atom will be present in that particular case, that the center is we call them as a that center is a chiral center. Okay, but where it will be RR and SS, in that particular cases we call them as a pseudo chiral center. There is chiral center will be there, but we can't say them as a chiral center, because in the both cases we have two different two same chiral center, and that chiral center, whatever the chiral carbon, that is same configuration. That's why, because of if you rotate the molecule, then there is chances that you will get, we call them as a chirality on that carbon or not. That's why the chirality will comes at some time, and also the chirality won't come at another times. So that's why in that particular case we call them as a pseudo chiral center. But if you have R and S, in that particular cases we call them as a chiral center. But if you have R or SS, in that particular cases only we call them as the pseudo chiral center. Yeah, this is for the chirality only for stereochemistry. Okay, these are not your course. Yeah, what will happen in these cases? This reaction is so much fast reaction that if you don't use that the any kind of solvent also in the net reaction, that we will get our corresponding product. Yeah, what will happen in this cases? Yes, yeah, reduction will get, and will get our corresponding data. Yeah, do you know that what is the name of this one? Yeah, iso pinnacle something. Okay, you don't know. Camphile boron. That's whatever CB is nothing. That's the camphile boron. That we call them as the diisopinacoil. That P means nothing but pinacoil. Okay, na? Ah, that is the camphile that boron. And whatever the structure that you have seen, from that structure only you will get your name. That's whatever you will get. And what is the name of this one? This one. Yeah, campaign. Are you sure? Yeah, my cursor is no. Maybe. Yeah, my writing is okay. This one. Pinene. Alpha pinene. Yeah, this one. Okay. Yeah, how it will react? Generally, how the hydrate will be transferred. That this one. This nothing but the configuration of this cyclic system, that the IPC nothing but this one, and it will bind to our corresponding that keto, and whatever that the dimethyl group, it always we call them the axial to that the CH3. Whatever this CH3 will be there from that it has to be comes from, we call them as a distant away from that the this CH3 group. Whatever the CH3 group will be there. Our call them as the whatever the gem dimethyl group. Suppose that if you don't have gem dimethyl group, then there is no chances because both center is same. And in that particular cases, our hydrate transfer will be there, and we'll get our boron. Whatever that the boron salt, and we'll get our corresponding that the alcohol. After workup, yes, okay. From that, this boron only that you can decide. So whatever that boron you have, that ITC boron, that whether it is plus one, minus one, from only that you can decide whether it will form from that the top side or the bottom side. Whatever that the boron stereochemistry of that one, yeah, that will always decide as from which side your attack will be there. Yeah, not that if you want to convert, suppose that if you want to convert this structure to this one, then you will get from that the upside. But if you want to see in a planar system, that's like that if you keep your ketone in a in a plate, and here that's whatever that's your methyl group, that is gem dimethyl group towards you, and whatever that another methyl group that will be there from that. Then only that you will decide from through which places your attack will be there. That you take your carbonyl group as a phase, that is planar. Then only which phases your attack will be there. Because that's whatever that's your gem dimethyl group. Yeah, that will be pointed from towards yours, and here when it will transfer proton. That's sorry, no, no, not proton. That's when it will attack that the hydrate one. Then it has to be that's that we call them as a whatever that gem dimethyl group. This group and this group. This has to be, and this both group has to be that's we call them as a further from that each other. And in that particular case, what will happen? That if you attack from that above phases, from this phases, then it will causes that the more steric index with that both the gem dimethyl group. That's why it has to comes from that the other phases to show that the 3D model that is not possible in, we call them as in writing. So to know that the 3D model, that's I have to show like that's why I draw that the structure in such a way that how the transfer like we call them as hydrate transfer will be there. In a always that's in Pinnacle at the IPC one. Here transition state for that the reaction is like this one. Yeah, this is the transition state. Okay, and how that's here in this case, a particular case, you will see that whatever this here the hydrogen, that this hydrogen one, this one that is present above, that hydrogen will goes to your carbonyl one. Then only you will get your hydrogen from above. Okay, that in that the whole process. If you see like that, but if you put this hydrogen in a plane, then first you have to keep your hydrogen in a plane, and your we call them gem dimethyl is above, and your that's another carbon that you have to place in a below position. That the bottom faces. This one. Whatever this hydrate that in that the reaction you will see. hmm, Whatever this hydrate transfer will be there, first you will check that whether that hydrate will be from the above position or the below, sorry, that the in axial or equatorial side. You'll see in this particular case it is from the other top sides. Whatever. Suppose that this hydrate that will present here, that whatever the structure of that the IPC, yeah, that will depend upon that the structure of this one. From this one only that we have drawn this one. This one is IPC structure and the most stable conformation of this one. When it will form a six-member transition state. That if this hydrogen will we will put this here, then the attack will be it's not more feasible that as compared to that's a if you put this methyl group in equatorial. That's why for a six-member chelated ring, this hydrogen has to be in a that the ring only. And in that particular case, your hydrogen comes from the above phases. That the above phases. That's like in IPC that it will be donated a that's our the hydrate from that above phases, and we will get our corresponding that the bottom phases alcohol. That you understand or not? Yeah, no. Whatever, sorry. That's, whatever that hydrate transfer that you will check from that transition state that whether it's from that the this phase because there is IPC and also that if you use that the plus one and minus one, then you will get different product. Na? In that particular process also that you will decide that the, which one you will get from this transition state only. So for this that no, the steric, if there is a steric factor, then you will get that different diastereomer. If there is any kind of chiral reagent is there, in that particular case, you will get a different enantiomer. Okay. If there is any steric factor, then you will get different kind of, we call them as the diastereomer you will get. If there, in some cases that in psychology, like that chair case system, or in the other cases, that you will get. Suppose your reaction will be from that the upper phases, or sorry, bottom or top phases, then you will get that the different kind of diastereomers. It's not like that you will get that the enantiomer, particular enantiomer. Okay, the diastereomer will get that. It may be possible from that the both phases also, but it will depend corresponding to that the other carbon. That if there is any chiral center or that any bulky group, from that bulky group only that will decide that which one will be preferred. But maybe that you can put that bulky group in that the top phases or bottom phases also, that will be possible. But in the asymmetric induction reaction, in that cases your chelation from that the catalyst phases, that will depend that catalytic binding to the substrate, that phases will decide from which the phases your attack will be happening. Okay, that your catalyst always decide that from which phases your attack will be happening. That's in asymmetric catalysis. Like in the asymmetric synthesis, that where you will get the particular kind of an answer. Okay, yeah, this is my yes, yeah, always, yeah. Boron will in that the previous cases also that this we call them as the CVS catalyst also decide that the which phases your attack will be there. Always your catalysis, not your that structure. But when that suppose that you have any in this particular cases, yeah, I will show you something. In this particular cases, suppose that you have in this we call them as ketone, this ketone, that's the alpha position, there is a chiral center will be there. Okay, the chiral center, chiral center, if it's above or below, whatever. In the particular cases, that if you don't use this catalyst, CBS catalyst, and you use only the sodium borohydride, that other kind of reducing agent, in that particular cases, your substrate will decide from which phase your attack will be there. Okay, okay, yeah. Okay. It will depend upon your catalysis. That the, so which catalysis, which kind of catalysis you are using. That we can't say always that we will get thermodynamically or kinetically. There is no rules that you will always get thermodynamic flow. Yes. Yeah. If there is a chances of that, that like that kind of stereo game, we call them a stereo isomer or that the different diastereomer will be for in that particular cases, that kind of we call them as a derived reagent that the modified reagent of that the borate they have used. Whatever you are saying is that is correct, but for asymmetric induction, for that's what I am saying is that for asymmetric induction that you need that your asymmetric that we call them as a chiral center that the generation of chiral center that is always depend upon your catalysis, not your reagents. Your catalyst always decides. Your always catalysis only decide from which phase because in the catalysis there is two phases because the catalyst control that the one phases that because if your catalyst is not chiral, then you won't get any kind of that the chiral moiety because from that catalyst only that you will get a chiral center. So that the from it will bind to your substrate and whatever the reagent that will be comes from that the we call them as one phases and another phases that will be blocked by our catalysis. Then only we will get our the attack from that the only one phases. But if you don't use any catalysis, then it will be attacked from that the both phases, and you will get a we call them as the enantiomer. Understand or not? I still okay. Yeah, yeah. It's already 9 that you can leave. Okay. Thank you. Maybe today only two people they have joined. Okay. Yeah, thank you. Okay. Good night.